Thank you, Heather, and thank you all for being here. I appreciate your interest on a Friday. Is it Friday? It is Friday. Friday evening. Not your typical Friday evening activity, but as it turns out, I was speaking at King's earlier today, and then the requests kept coming. Can you also speak somewhere else later on that day? And well, 6 o'clock sort of was the last possible moment that we could squeeze in. So here I am, and I apologize for not being able to stick around and chat afterwards, but I do plan to leave enough time for questions. Here's the outline of what I plan to talk about with you this evening. So the title is Quantum Physics and Christianity. I'm going to explain a little bit about what quantum physics is. I'm not assuming everybody here knows what quantum physics is. In fact, I just wouldn't mind a show of hands. How many of you have taken at least one course at the university level that deals with quantum physics in some way? Okay, that's pretty good. That's probably the largest group that I've seen at events that I've been at. I've been in Halifax, Ottawa, Montreal, Toronto, Winnipeg, and yesterday Calgary doing this sort of thing. And there's just always a broad demographic of people attending these lectures, so I'm interested in hearing what kind of questions you have and hoping to give you some insight into the way we understand what happens at the microscopic level. So I'm going to do a brief quantum physics primer by doing some demos in quotation marks, because I don't actually have the materials for the demos here, which would include a Geiger counter and some radioactive sources, as well as a few sources of light and prisms and that sort of thing. So instead of doing them as actual demos, I'll just put them on the screen for you to see. And I'll talk about the different ways in which that quantum physics, the advent of quantum understandings, have changed the way we think about the world, has shifted our worldviews. And then I'm going to spend some time talking about determinism and indeterminism. And I'm really sorry that our main original host for this evening, who's Don Page, who's like one of the world's top quantum physicists, is actually unable to be here all of a sudden at the last moment. Like 2 hours ago, he called us and said, "Sorry, I can't make it anymore." And so you saw us scrambling to get everything connected. He was going to do that for us, but we managed to get it all connected. And so he actually told me that he disagrees strongly with my views on determinism and indeterminism. And so I was hoping to have a bit of a debate with him, or actually more to be informed by him about those matters. And so I will try to explain maybe what he would have said if he were here. So that's a bit of that's the quantum physics primer, end of things. And then I'm going to do some theological and philosophical reflections that are around the matters of quantum physics. So first I'm going to do some general remarks about creation, covenant, and law, which are very general ways of seeing connections between science and Christian faith. And then I'm going to focus in on indeterminism again, and connect that with some different theological perspectives about that. And then I'm going to go and have what I think and what people have said are the funnest parts of the talk, and to explore something called quantum field theory, and some interesting things about how quantum field theory is in some way an echo of even human relationships and even Trinitarian relationships. So going quite exotic, I think. And then ending with some reflections on biophysics. One of my areas of research is theoretical and philosophical biophysics, where I will discuss a little bit about how electrons and the quantum world is related in some way to biology and also to agency. So the quantum physics primer. So I'm going to do two demos in quotation marks. The first one is about different kinds of spectra, and the second one is about nuclear decay. And these demos I'm doing because they, I think, will show you that the effects of the quantum world are visible and audible at the ordinary levels that we can experience. And so rather than just being something that happens deep inside some lab somewhere in some mysterious way, these are things that we can actually see and hear. When we have a beam of white light and pass it through a prism, everybody hopefully has done that sort of thing at some point, and you see that there's a continuous spectrum that comes out of that prism. The prism shows that in fact the white light can be analyzed into that whole spectrum, ranging from the violet over to the red. It's a continuous spectrum. That's, I guess, the key point here. But when we take other kinds of materials and other kinds of light, like a hot gas or a gas through which electricity is flowing, then that gas emits light as well, and when we analyze that light, that is, put it through a prism to see what it is composed of, we see that instead of being a continuous spectrum, there is a discrete spectrum. And so that is sort of a signal of the quantum reality. So quantum physics, the word quantum deals with quantity and counting and that sort of thing. And so you can count how many colors are here. There's 4 colors in this spectrum, and you can't count how many are over there. That's a continuous spectrum. And so being able to say a discrete number of things, that's sort of a kernel element of what it is to be quantum. So the quantum physics is, in fact, quantum physics is needed to explain this quantized emission spectrum. As it turns out, for reasons that we won't get into in this talk, perhaps in the Q&A, quantum physics is also needed to explain the continuous spectrum. But the point here is that introducing the idea of discreteness and individuality is going on. So the next demo, which if I had a radioactive source and a Geiger counter, you would hear click, click, clickety, click, click, going on.
Now, I'm going to do another demonstration that involves you listening. I think we can probably listen well enough. We're going to listen to the beta decay of strontium 90. So here on the floor, I've got a little green piece of plastic, and in that piece of plastic there is some strontium 90, and I'm going to turn on my Geiger counter. So this is a Geiger counter that actually was given by the biology department. Interestingly enough, the biology department had extra Geiger counters laying around, and so if you listen carefully, you can hear something, right? And so it clearly has something to do with how close this green sample is to this thing over here, and things change. You know, if I put a thumb in front, so now my thumb is absorbing the radiation instead. So what I want to illustrate is that the sounds are not nice and smooth and continuous. There's individual signals that are coming, and you can't ever predict a pattern. There's not going to be a normal pattern of, every second it's going to go like click, 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 click. It's going to be always random, right? So if you try to listen for a pattern, you're not going to notice a pattern. But we'll be able to notice certain patterns, like that the number of clicks per minute may be a certain amount. At this distance, it'll be a different amount. At a different distance, and if we did this 30 years from now, it'll be about half of what it is. So this is strontium 90. So this is a sample. This is a strontium 90, which has a half-life of about 30 years. So that 30 years from now, if I were to come back and do this again, we'd hear about half the number of counts as we're hearing now. So that's a little demonstration of quantum physics, of nuclear radiation. And so this nuclear radiation is occurring as strontium 90 turns into yttrium 90, emits an electron and also an antineutrino. And it's the electrons that are being emitted by the strontium 90 that are getting noticed by this Geiger tube and getting turned into an audible signal that you can then hear with your ear.
So I'm going to be simulating 4 identical samples of 2 different sizes. So in the boxes on the left, I've got 4 nuclei in each box. And over on the right, I think I have like 400. I didn't even actually count, but I think it's 400 nuclei in each of those 4 boxes. And then we're going to let time pass as these nuclei undergo radioactive decay. So some nuclei, as you likely know, are prone to nuclear radiation. So they will decay. So carbon-14 turns into nitrogen-14 over time, with a half-life of 5,760 years, which we use to date biological samples, for example. So, and the meaning of that half-life is that in that time period, half of the nuclei would have decayed. If you wait another half-life, then by then another half would have decayed, leaving only 1/4, etc. And so on the top of the screen, you'll see a number which tells you how many half-lives have elapsed as the animation goes on. So I'm going to do an animation, and you can watch the animation because it will loop around and around and around. And if you're so interested in that, you can just watch that and ignore what I'm saying. Because it's kind of fun, I guess, to just watch the thing. But I want to use it as a demonstration of what the quantum world is all about. What are some of the features of the quantum world? So as we take now these starting boxes of 4 nuclei or 400 nuclei, we're going to let time pass, and then we're going to see what happens to them. And so, of course, this is a simulation. This is not what a nitrogen or a carbon atom looks like, right? But I'm just using that as a simulation. So and what's going to happen is the blue dots will just disappear. So when they disappear, that means that they've undergone nuclear radiation. So there's the running of the sample. So there we go. We can see as time goes on, decay is occurring. Then we have up to 4 half-lives have cycled through, so you can keep watching that, I suppose, over the rest of the time. I can leave that on the screen. So I'm going to demonstrate, or talk about the 4 key features of quantum physics that are demonstrated in these, in the phenomenon of nuclear decay. And the first one is discontinuity. So we have these nuclei, which are in 2 possible states. They're undecayed and they're decayed. So there's not a slow transition from the undecayed to the decayed. It just happens discontinuously. So the blue dot does not sort of slowly fade out, but it boom, suddenly decays. So that's one element. So there's the discontinuity, again, which is similar to the discontinuity that we see in the spectrum, the quantized spectrum. We also see this notion of individuality. Each sample is doing something unique to itself. So this sample over here decays in a certain pattern. This one first, and then that one, and then that, and then those 2. And it's done. Right? This one over here never even got to decaying those 2 over there. And each of these boxes is doing something different. It's doing something that is individual to itself. There's also randomness. So we can see that there's not a nice pattern of the decay occurring like from the top left and then over down to the bottom right. So it doesn't just sort of clear off like we might wipe the slate clean, but it's random. You just look over there and you can't tell where the next one's going to go, when the next one will decay, which one is going to go next. There's no way of predicting that. It's not totally random in the sort of everyday common use of that word, random, which means having absolutely no pattern and completely arbitrary, but there are patterns. And so the pattern is kind of illustrated by the fact that there's a half-life in the first place. We have that half of them, on average, would decay in 1 half-life, etc. But not exactly half in each case, but we can talk about the probabilities of the decay in accordance with that half-life. But within those probabilities, they remain probabilities with that randomness. And then finally, we have this business of indeterminism. Indeterminism is the idea that knowing everything about the original sample is not enough to tell us what will happen to that sample over time. So in fact, each of these 4 samples are identical to each other, but yet different things happen to each different one. And similarly for these ones over here. So even if we knew absolutely everything, in fact, we do know everything, in a sense, about each of these nuclei, and they're all identical, but there's nothing that would just differentiate this one and this one, yet this one, there, it decays, right? And the other one didn't after 4 half-lives. This is the idea of indeterminism, which says that knowing everything about something now is not enough to tell us what will happen in the future. So these are sort of 4 key elements that are demonstrated in cases of nuclear decay, and they're kind of common to a lot of things that happen at the quantum level. So at the quantum level, what I mean is we're talking about down at the scale of atoms, maybe molecules, certainly electrons, neutrons, protons, and that sort of thing. So along with this development of understanding of what's going on, which happened mostly in the early 20th century, like in the 1905 in a sense, or 1899 might be thought of as the beginnings of the quantum understanding. In 1905 we developed significantly. In the 1920s we learned a whole lot more. So the early 20th century is when quantum physics really came on the scene. And along with that, there arose a new way of seeing the world. So that the older way of seeing the world, at least in its sort of physical manifestations, in the way that things happen on a physical level, would be described as Newtonianism. So Isaac Newton, his laws of physics, F equals ma, etc., Newton's first, second, and third laws, Newton's law of gravity, etc., all of those laws gave us an idea of how things interact with one another in the universe, how things move and how they accelerate. That had to change a lot through the advent of quantum physics. And so I'm going to just walk through the number of changes that have occurred to the way that physicists at least think about the world. And in many ways, popular culture hasn't really caught up yet to that. Many people in our everyday experience still think of the world in a Newtonian sort of way. But in fact, actually, many people still think of the world in an Aristotelian way, which is back to Aristotle, even before Newton. So we're kind of like, in some cases, asking you to jump a couple of steps forward in our understanding of the world. So I already saw this shift of continuum to quantum, so that things which exist on a continuous way, they show up as a quantized, in a quantized way in the cases of the quantum world. So other things are also discontinuous. For example, the energy that a particle can have. If we look at an electron in a hydrogen atom, the electron can't have whatever energy it wants. You can't take an electron and speed it up a little bit and go a little bit faster, or a little bit faster, or a little bit slower. We can't make those small adjustments. The adjustments that we can make to energy are discrete. We can only ever make an electron in a hydrogen atom or any other atom increase by a definite amount. If we try to push it a little bit harder, it won't even respond at all. But we have to push it a lot harder and exactly a certain amount harder, and then it will actually jump to a different energy level, which is quite different than how you drive your car, right? When you're driving your car, it's not driving along at 10 kilometers per hour, then suddenly at 15 kilometers per hour. I mean, maybe if you have a really bad speedometer, that might happen, that your scale would kind of show that. And most cars now actually have quantized digital speedometers where it's saying that you're going from 31 kilometers per hour to 32 kilometers per hour, which of course is not happening. You're actually going slightly faster all the time, but then your scale, it just sort of says 31, then the next number is available, 32. So if we actually traveled 31 and then our next speed was 32, we would feel a jerk. And that would be a quantum jump in energy. And that's the kind of thing that happens at the quantum level. Electrons and molecules and atoms behave in that sort of way, that they jump in their energies rather than smoothly transition. We also had a world where we could be quite certain, or at least we thought we could be certain, and we had the idea that if we do a good job of measuring, we could eliminate our uncertainty. So that is the idea that if we wanted to measure where something is, we had the idea that we could measure it very, very precisely. And by the end of the 19th century, people were getting super confident about physics being almost complete, that all we needed was just measure some things with even less uncertainty, more precision, and settle the matter. So where is something? How fast is it going? Well, those questions can be answered with increasing certainty as we develop better and better technology. As it turns out, the quantum world forbids that sort of thing. The electrons that we're measuring the speeds of resist that operation. They resist our attempt to measure their location precisely, and also their speed precisely. In fact, the more we know about one of them, the less we can know about the other one. So if once we start knowing for sure where something is, we know less about how fast it's moving. If we know really precisely how fast it's moving, we hardly have any idea where it is. So this is called the Heisenberg uncertainty principle. And so we shifted from certainty to uncertainty as we entered the quantum era, in a sense. So some of you perhaps have had speeding tickets. You can raise your hand if you want. Okay, nobody in this room has ever gotten this. Okay, wow. So on your speeding ticket, it might say something about how fast, what day it was, right? Or what time this offense occurred, and the location of your speeding ticket, like which intersection was it, and also your speed. Right, so it says how fast you were going and where you were. And so Heisenberg's uncertainty principle says you can't know both exactly where you were and how fast you were going. And so you should perhaps take that ticket to court to the judge and say, I'm sorry, Judge, I know that this didn't happen because this ticket that I've received violates Heisenberg's uncertainty principle. It tells me where I was and how fast I was going, and we can't know those things. So if you try that, let me know how that turns out. Stories of that. We also went from a world where we could predict things. Sorry, I missed one. The dualism of a particle wave. So through the development of classical physics, the Newtonian physics, we realized that we can describe objects and we can describe waves. So if we throw a pebble into a pond, we see ripples flowing away from that. Pebbles we can describe in one way, and ripples we can describe in another way. So pebbles, they obey ordinary laws of motion, force equals mass times acceleration, and we have nice ways of calculating all of that sort of stuff. And waves, well, we have to describe them in a different way. We have to develop a wave equation, and we also see that waves interfere with each other. Two waves can cross each other, go through each other without getting destroyed. Right? They can just carry on after they go through each other. They undergo constructive and destructive interference, so waves can cancel each other out and that sort of thing. And if you wear noise canceling headphones ever, like if you have loud kids at home or you're flying on an airplane, then you put those things on, and what they're doing is they're actually sending sound into your ears that actually cancels the sound that's otherwise coming into your ears. It's adding a wave to the incoming wave, and they cancel each other out. And so that's a property that waves have, and particles, sort of, we think, don't have those properties. Rocks, you don't have two rocks that come along and poof, suddenly they're gone, right? That's our ordinary experience. And two people walking into a room and bump into each other don't annihilate each other, usually, right? If there's maybe strong disagreements on a theological level, maybe they sometimes do. They shouldn't, I suppose. But anyway, as it turns out, the world is a bit different than we had expected from the classical understanding. We realized that things that we knew for sure were waves. Like in the 19th century, we discovered that light is a wave, and we had very good demonstrations of that. Light undergoes destructive and constructive interference. In the early 20th century, it was also shown that light is actually a particle. So light has particle behavior, and in fact, Einstein got his Nobel Prize by explaining the particle behavior of light. So waves are particles. That is, light comes in chunks, in individual, discrete pieces of energy. And things that we thought that we knew for sure were particles, like electrons, which come sort of one at a time out of an electron gun, or they come out of nuclear radiation. Those things are known to be particles. We can calculate their mass and their speed, and they hit each other, and they have momentum transfer, and all of that sort of stuff. Well, we realized after a while that actually those particles have wave behavior. They have the ability to cancel out. They have the ability to sort of divide and go through two different places and then combine together and give a wave pattern. So we started to realize that the things that we thought were particles actually have also wave character, and the things that we thought were waves also have particle character. So the world, instead of being a world of particles or waves, is a world of things which have particle and wave character. So there's this duality between particles and waves rather than as sharp dualism. So a lot of you have taken high school physics, at least, perhaps, or maybe you've heard of people who've taken high school physics. Maybe you've pitied them, and so you've had to do questions like, the batter hits the ball, and the ball starts off at home plate with a speed of 42 meters per second at an angle of 35 degrees, and it was hit from a height of 1.2 meters, and so how far from the home plate does the ball land? Did the guy get a home run or not? And so you were able to calculate those sort of things, or at least you tried or pretended to calculate those sorts of things, or you wished that you could, or you copied over someone else's who did. Whatever it was that you did in high school physics. No, we're not going to blame anybody for their high school behavior. But we were able to predict things, and we did pretty good jobs of being able to predict. So knowing where something is at the beginning and how fast it's moving, we can predict where things get to, and we thought that maybe we could do that for the smaller scale stuff too, and we realized, however, pretty soon that that's not the case. If we take an electron gun, which we can rig up to send one electron at a time toward a screen, then we ask the question, where does this electron end up on the screen? Well, we don't know. All we can say is that we can calculate the probabilities. We can calculate, there's a 20% chance that the electron will land over here on the screen, and then there's a 0% chance it will land over here, and a 10% chance of it landing over there, etc. And so we could develop a pattern that tells us what the probabilities are for the electron landing at various parts of the screen. So instead of being able to predict things, individual events, all we can do are talk about probabilities, and we saw a bit of that in the nuclear case that I was describing or demonstrating earlier. So we went from a world of being able to predict everything, a Newtonian world, to a world of the quantum world, where the best we can do is to tell you probabilities. We went from a world of determinism to indeterminism, and I'll say more about that in a minute. We also went from a world where we thought that scientists were objective. That is, we watched the world happen, and all of the events and things in the universe did their things, and we watched and sort of took notes, and we wrote down what they did. we were objective observers of the universe. Quantum physics, however, shows us that we are intrinsically subjective participants in the world. So we have to be involved in the world, and our questions actually affect the answers. Well, I guess that's sort of obvious, but more the point here is that questions affect the behavior. So depending on what kinds of questions we're asking and what kinds of observations we're making, the behaviors of the systems that we're studying actually change. And so if we use, for example, a two-slit experiment where we would send light through a screen where there's two openings, and then the light recombines to form a wave at the other, a wave pattern on the other side of that mask or barrier, then we might ask the question, through which slit did the light go? And as soon as we ask through which slit it went, we find that if we try to determine that, we actually destroy the wave pattern that results. And so the kinds of experiments that we do on electrons, for example, or on any microscopic particles, we see that the kinds of questions that we ask affect the kinds of answers that are available, and they affect the behavior of the system. So in some mysterious way, electrons and particles in the quantum world are a bit more like children than they are like stones. I think you know perhaps that children act differently when they know they're being observed than when they don't. Well, it turns out electrons also behave differently when they are being observed. It's not their knowledge of, they don't know that they're being observed, but yet somehow their behavior is changed by our active observations. And one of the acts of observation involves the collapse of the wave function. So the wave function is in a sense the set of all the probabilities that could exist. So if we take an electron, aim it towards the screen, I can tell you the probabilities of it landing at certain spots, and that collection of probabilities is described by a wave function. When the electron actually lands on the screen, then it's no longer some bunch of probabilities, it's an actual particular event that has actualized. So there's a transition from set of probabilities to the actual event. And that is called the collapse of the wave function. So the standard interpretation of the collapse of the wave function is that it occurs upon human observation of an event. And so I've got a picture here of the Schrodinger Cat Experiment. So if there's any cat lovers in the audience, maybe you want to just close your eyes and ears for a little while, because some cats may or may not be hurt in this little demonstration. May and may not. Okay. So here's the setup. And Schrodinger used this setup to kind of show that quantum physics is way off base. Somehow it's just totally crazy. So what we do is we take a cat and put it in a box, in a sealed box, and a box that you can't even hear anything going inside it, so it's totally sealed and enclosed. And also, along with that cat, you put a bottle of cyanide, and above that bottle of cyanide, you poise a hammer, which is connected by a string, to a lever, which is connected to a Geiger counter, which is measuring the nuclear radiation that's occurring inside that box. And so, in this box, we have it rigged up so that after 1 hour, there's about a 50% chance that the Geiger counter will have registered enough counts to cause the lever to flip and the hammer to fall and the cyanide to be released and the cat to die. And so the way that we understand the state of the nuclei is that the nuclei are described in a state of being 50% decayed and 50% not decayed. So that is, we're not saying that they have decayed or that they haven't decayed, but they exist in a state which is sort of a mixed state of 50% decayed, 50% not decayed. I don't mean that 50% of the nuclei have decayed, but I mean that there's a 50% chance that the nuclei have decayed and a 50% chance that they haven't. And so that's the state. That's the best we can say quantum mechanically about the state of the system. It is that combination of probabilities. And the standard Copenhagen interpretation of quantum mechanics says that nothing specific happens until we actually open the box and look inside it. So a human being opens the box, and humans are incapable of seeing cats in a mixed state of dead and alive. And the idea is that our active observation forces the cat to then be alive or to be dead. And then all of the previous events sort of also are suddenly actualized. And so that's the the Copenhagen interpretation of quantum mechanics. Maybe I should tell you my interpretation of quantum mechanics, because I don't quite go along with that and I think many physicists don't really quite go along with the Copenhagen interpretation all the way. One of the solutions to this is that it doesn't require human observation to cause the wave function to collapse, but it requires something which is big enough to make a change that can't happen, can't go back to the way it was. So this is called a macroscopic irreversible registration of the quantum event. So if the lever falls, that's it. Then something has happened, and then the cat is dead. So if we didn't have a way of doing that falling of the lever, then we could maybe say that the state does exist in the mixed state. But once there's a lever involved, which is a large object with 10 to the 25 atoms in it, that lever is a large enough object that it can't maintain that quantum coherence. So the collapse of the wave function is an example of, at least the Copenhagen interpretation is an example of how the importance of the human as an observer. We also went from a world where we thought we could reduce everything down to individual particles doing their own things, to a world where we recognize that there are more connections between particles than we might otherwise have expected. So there's a slightly more holistic approach. So we see that there's connections between particles. In fact, we have situations of entanglement where we can create a state, a quantum state, which even when the particles are really far apart, they behave in ways that show that they are somehow connected in some perhaps mysterious way. People have made perhaps too much of that and assigned words like spooky to this. In fact, it's called the spooky action in a distance. That's, if you look that up, that's the term that we use for this. We also went from a form of realism which was kind of naive to a more careful or critical realism. So that is the way we think of the world. And I think scientists are realists. We think that the things that we're describing in our theories and experiments actually exist. Kind of silly, but we think they exist. And the naive realists would say they exist in the very same way that our theory describes exactly. And they exist in ways that, like, small things are just like big things, etc. And we're now trying to be, I think, more critical in our realism and say, the ways that the world is slightly more unknown to us, and we need to be careful to not assume that our large-scale understandings apply down to the smaller scale. So I'll talk more about that a bit later as well. So those are some of the ways that the world view, our view of how the physical features of the universe function, have changed as a result of quantum physics. A bit more about determinism and indeterminism, which I kind of skipped over a bit. So these two words, they have several syllables, determinism and indeterminism. Determinism just is the idea that the future of the universe is fully determined by the current state of the universe. That is, by the end of the 19th century, the idea was that, and this was the idea of Laplace, who said that if I know where everything is, where every particle is, and how fast every particle is moving, and how those particles interact with one another, I can predict, in principle, where those particles are going to go in the future. The whole entire future is all settled once I know the present state of the universe. So the idea was that everything is made of those particles, including our brains, and our thought processes are in some way, of course, intricately connected in some way with the motions and positions of the particles in our brains. And so every single future event is already determined by the details of what the present situation is. And so that idea is called determinism, and it was quite the standard way of thinking of the world at the end of the 19th century. Indeterminism just says that's not true. And so I guess this was the way of looking at the world, and I think this is largely the way that the world is thought of now. And that's partly because of modern physics. So quantum physics, I think, shows that determinism is not scientifically tenable anymore. So if we used to think that the world was deterministic, after all we had were Newton's laws, then we could perhaps imagine that the universe's future is fully determined by the present of the universe. There are different interpretations. Okay, so different people do say different things about this. In fact, Don Page would probably disagree with me on this point, and I wish he was here to tell us exactly why. But he brings up a few oppositions to the idea that quantum physics is indeterministic, and he would say maybe it is deterministic after all. I still think that even if quantum physics is indeterministic, even if quantum physics is deterministic, the world still is indeterministic. Because after all, perhaps I think quantum physics doesn't fully describe everything about the world. So that's why my response would have been to Don Page, and maybe he'll watch the video afterwards and let me know what he thinks about that. So there are many different ways of interpreting quantum mechanics. I already suggested one of them in terms of the Copenhagen interpretation and the requirement of human observation versus macroscopic irreversible registration of a quantum event. And the same thing happens for determinism. There are people who are working on deterministic models of quantum physics. I think it's a kind of a failed project, and I think in addition to that, it's kind of cool to me as a Christian that science also shows that the world is indeterministic. I think that Christianity kind of implies that the world is indeterministic. That is, knowing everything about the present state of the universe is not enough to tell us what the future will be. We have actual choices to make in this world. So our actions in the world actually have an effect. Our choices and our decisions change things in the world. God calls us to act responsibly, and He gives us certain requirements, and we have to follow those requirements. Sometimes we don't. Usually we don't. But we have those choices, and those are real choices that we really have, which are not simply us going through the motions that are already there for us as determined by the present state of the universe. If in fact the present state of the universe determines the future of the universe, none of us have anything to do. It's just all automatically happening anyway. That's really fatalism. So there's an interesting resonance, I would say, between Christianity and modern physics in terms of this indeterminism resonance. Not a proof or a demonstration. I'm not saying, ha-ha, now we know that Christianity is true, because quantum physics has demonstrated the world is indeterministic. I would never say that. So there's just an interesting and curious echo or resonance, and I'm going to get to more of those a bit later on. So there are different ways of interpreting indeterminism, and I'm just going to put up three different philosophies of science and how they might think about indeterminism. One of them is the naive realist. So the naive realist, who I talked about a little while ago, would say something like this: well, the world really is deterministic, and there's just a human ignorance which is temporary, and we'll eventually take care of that. We'll just get smarter and better. Now the instrumentalist says the science doesn't really describe anything about the actual world. Science only gives us tools to be able to sort of handle and cope with life, and to maybe make instruments, to build devices. And so instrumentalists would sort of say, who cares whether the universe is deterministic or not? And maybe there's some inherent limitations, like experimental limitations or conceptual limitations, that eventually will be taken care of. But it actually doesn't really matter, because science doesn't describe the world anyway. The critical realist would say something like, well, if we are seeing this in our theories and in our experiments, then maybe this is a real thing. This indeterminism is really present in the world, and there really are different possible paths for the universe to unfold as time goes on. So now I'm going to shift a little bit to talking about some general remarks that I would have about how science and Christian faith work together, how they relate and how they integrate. We know that science, in a sense, studies regularities. There are also irregularities that science studies, like those randomness patterns of decay and so forth, but even that we look for relationships and patterns of decay. So in general, I would say that science looks for trying to explain patterns of regularity. Where do these patterns of regularity come from? Science simply has to assume that they're present. We observe that they're present, and we study them. And our observations don't make this requirement, don't require the universe to have regularity. We're simply noticing these regularities. I would say that as a Christian, the world has, I would say that I understand why the world has these regularities, and I would say it's because God is the creator, and He's created a world with these regularities, and He's made a covenant with creation to continue these regularities. And so God has told us, and He's sort of spoken to creation in Genesis 8:22, for example, as long as the earth endures, seed time and harvest, cold and heat, summer and winter, day and night will never cease. God is saying there will be these patterns of regularities that will continue. And as scientists, we can study those things with some confidence that those patterns will continue. Not that everything will continue unchanged in the future entirely. There is development and change, of course. But there are going to be these patterns, and we can trust that God will maintain these patterns because we believe that God is faithful and good, faithful to His covenant. Another thing that I think about in terms of science and Christian faith is I think about two different kinds of laws. So in terms of physics, there are laws of physics that, we've talked a little bit about F equals ma and Newton's law of gravity and so forth. And all of these laws of physics have certain characteristics, and I've listed out on the left-hand side of the screen some of the characteristics of those laws of physics. And on the right-hand side of the screen, I've got different kinds of things. I've got what I'm calling God's laws for physical reality. So on the one hand, there are human-formulated laws, and over here we have that God actually governs the creation in some way, and there are different characteristics. So one of the main characteristic, I would say, of the way that God governs physical reality is that there's a covenant of God that I just talked about a minute ago. And we saw that math is important in physics. Laws of physics are expressed with mathematics. The laws of physics describe the world. God's laws prescribe the world. God governs the world in some way that actually makes the world have its behavior. When we write down F equals ma, we don't make mass accelerate by a force. We just simply are observing and describing the patterns that we see. The laws of physics keep on changing because we're doing a better and better job of understanding the laws of physics. And I think the way that God governs the creation reflects something about God to us. So they reveal to us something about God's character, God's faithfulness. I already talked about God's power and knowledge and wisdom, etc. So this is part of my understanding of thinking about laws of physics, how they relate to how God governs the world. And I would say that I don't agree with Kepler. Kepler says that we think God's thoughts after him when we are doing and discovering work, our studies in the sciences. In a sense, these are God's thoughts, but they're quite mysterious. And when we're developing the laws of physics, we're not just sort of trying to copy exactly how God thinks about the world. We're trying to develop our own understandings and to do a better job of that understanding. Okay, so another big element of my thinking about how science and Christian faith relate is that not only did God create the world and establish these patterns of regularity, but Jesus Christ sustains the cosmos. So in Colossians 1:17, Jesus Christ is before all things, and in him all things hold together. Hebrews 1:3, Jesus Christ is the radiance of God's glory and the exact representation of his nature, and upholds all things by the word of his power. There's this holding together, holding things up. These are things that Jesus Christ is doing. It's not simply something that has happened in the past, but it's something that is an ongoing activity of God in terms of the creation. God is actively working to sustain the world. The idea here is that if God were to turn his attention away from the universe, then it would cease to exist. It wouldn't just simply start flying apart, but it would cease to exist because of the sustaining power of God. One of the ways that in my Reformed tradition this is expressed is in the Heidelberg Catechism, answer 27, where it's describing something about the providence of God. It describes God's providence in this way. God's providence is his almighty and ever-present power, whereby, as with his hand, he upholds heaven and earth and all creatures. And there's a metaphor here of the hand being used by God to uphold the earth. Right? I guess that upholding is coming from Hebrews 3. Christ is upholding things, which of course is a metaphorical way of speaking, upholding something up. But there's a really interesting, and this is like a conceptual echo, if you will, or a metaphorical connection or a resonance between that idea and something that we see at the quantum level as well. So at the quantum level, we're talking about atoms and how they exist, and one of the early models of the atom is that there's a nucleus with electrons orbiting around. And when electrons orbit around a nucleus, they're moving and they're accelerating, and things that accelerate give off radiation, and they lose energy and they would slow down. And so there was a serious concern among the scientific community as they were discussing this model and saying, well, why then doesn't the electron just sort of spiral in and stop and crash into the nucleus? In which case every chemical element would just quite quickly become nothingness, and the universe and life and everything in it would be gone. So it turns out that quantum physics shows us that this is not quite how the atomic structure works. there is in fact a lowest possible energy. So I mentioned that there are these discrete levels of energy. In fact, not only are there discrete levels, but there's also a lowest level. The electron in the hydrogen atom can't have any energy less than, well, negative 13.6 electron volts. If it tries to have less, well, it can't try. It just doesn't ever get any less. It has that very bare minimum. That's called the 0-point energy, and it describes the energy of the ground state of the electron. And so one way I think about that in a sort of metaphorical sense is that God is kind of saying, holding the electron up as with his hand from getting any lower in energy. I mean, this is just a metaphorical way of thinking. I'm not really thinking that God is somehow concentrating on that electron, watching out that it suddenly doesn't just zip down to the nucleus, but God has set up these patterns of regularity so that the electron is held up by his providence. So I talked about the uncertainty principle earlier with that traffic ticket, right? Whether we can know really precisely where the electron is and how fast it's moving. And so one of the classic Christian approaches is to think about the omniscience of God. God knows everything, right? And so we don't know where the electron is and how fast it's going with infinite precision, but surely God knows, right? And so this is the thing that I want to address for a little bit now. And my thinking on this question has been formed largely by the work of Dick Staflow here. Wrote a book called Time and Again, a book on the foundations of physics from a Christian reformational perspective. It's a 36-year-old book. I've met and spoken with Dick Staflow a number of times, and I am convinced by his explanation. And his answer to this is effectively the same as the answer to the question, well, if God knows everything, then he also knows the color of the number 2. Can somebody here tell me what the color of the number 2 is? I don't think so. Maybe some of you have synesthesia, and so you actually associate a color with every number. That's possible. But I understand that different people who have synesthesia actually have different numbers for different colors for those numbers. So there isn't a color for the number 2. And similarly, Staflow and I would say that the electron doesn't even have a position and a momentum. So what is more going on is that the position and momentum are properties of laws that we use to describe these things. So when we think about the quantum world, we have to be careful to not assume that its behavior is the very same as the behavior of things that we're used to. So we develop Newtonian mechanics, saying that stones are somewhere and they have some speed, and who are we to say that electrons also have to behave in that same way? After all, we want to be critical realists, and we have to be careful to not make those reductionistic sort of claims. We can't reduce the behavior of an electron to saying that it has to be the same as the behavior of stones. So those things like position and momentum are actually properties of laws, properties of things about our descriptions more than they are about the particles themselves. So this is an example of reductionism. So we're trying to describe an electron, which is really a physical interacting thing. I'll talk more about the nature of the electron pretty soon. As if it were simply something that we could give a number to and say, this is where you are, and this is how fast you're moving. And there are other examples of reductionism that are also worth opposing. For example, thinking that biology and all of its questions can be solved by physics. That's another example of reductionism. Thinking that our tools in one discipline will totally explain the questions of another discipline. Those other disciplines actually exist, and they have their own methods and their own language and their own things that they describe. So just for a quick example, if we are studying human anatomy and thinking about the function of the heart, what does the heart do? Well, it does all kinds of things, but its purpose is to pump blood, right? And physics doesn't have the category of purpose. There's nothing in physics, none of the physics textbooks that I've ever read or any physics papers talk about purpose. It's not something that we discuss in physics. There aren't any tools and techniques in the field of physics for that. So we have to be careful to use the tools and techniques of a discipline for answering the questions of that discipline. And the same thing applies to even just using the tools and techniques of one scale and applying them to a smaller scale. So John Polkinghorne, who I gather spoke here in 2004, I think someone was saying, referring to him being here, not that being here around then. He says something similar with longer and fancier words than I did, he would say, the veiled reality of the quantum world must be encountered on its own terms and in accordance with its Heisenbergian uncertainty. There is no universal epistemology. It would be epistemically disastrous to try to insist on the Newtonian clarity that we can often attain in the macroscopic world of everyday phenomena. So the point here is that we have to be critical realists and use the tools and techniques that are relevant to the things that we're trying to study and let those things present themselves to us, and we have to deal with them on their own terms. We should not force upon electrons descriptions that worked well for cars. So now I'm going to talk a little bit about indeterminism again and thinking about theological perspectives on indeterminism. And I'm perhaps going to caricaturize a little bit here, where I'm going to put on the left-hand side of the screen sort of a really left-wing or ultra-liberal perspective, and over on the right-hand side of the screen I'm going to put some right-wing or ultra-conservative perspectives. I hope that nobody's going to be offended. Some of you might find yourselves agreeing with one or two of those sides, and hopefully by the end of the day we can still leave happily from this room. So on the liberal or left perspective, there would be the idea that the future is truly future even for God, and indeterminism is absolute, and even God doesn't know what will happen, and He's ultimately helpless. There are actually people who say that their faith leads them to this kind of thinking. On the right-hand side, we have the idea that God created the universe with the future already all present and all laid out, and all we're doing is we're going through that. So the passage of time and even uncertainties and so forth are just human limitations, as we're stuck within this ability to only see one moment of time at a time, and to run through that sequentially. It's already all there. Furthermore, the laws of physics that these people are thinking about are prescriptive laws. There are actually laws that make the world behave the way they are, and they are the laws of nature that we are working on and discovering. And cause and effect is really ruling the show, and chance is one of those kinds of causes. It's just an irreducible cause. On the right-hand side, scientific law only ever describes things. It doesn't even explain, it simply describes. And there isn't even any real cause and effect in the world. The world just does what God makes it do, and causes and effects are not found actually in the world. That's sort of a really right-wing perspective, I guess. So some of you perhaps have studied theology, and there's a couple of words that describe these two, and one of the word on the left would be immanence. That is, overemphasizing God's presence within the world is overemphasizing immanence. And on the other end, we're overemphasizing transcendence. And so on the right-hand side, we're saying, God is outside of the world. And on the right-hand side, on this side, we're saying, God is actually within the world. And so how do we resolve this sort of spectrum of thinking of things? And I think the answer to the question, is God immanent or is He transcendent? For me, the answer is yes. God is immanent and transcendent. And so somehow both of these are getting something wrong, and they're missing something. And I don't have a full explanation for all of this, but here are some of my preliminary thoughts about this. So I believe that the Bible actually, and our experience actually shows that God is both transcendent and immanent. God created time, but yet He also joins humanity in our experience of time. He goes along with us, He's interacting with us. God is described in Scripture as a personal God, a tri-personal God, and as a person He's interacting with us, for example, through prayer and answering prayer. And furthermore, particularly thinking about the incarnation, Jesus Christ, the second person of the Trinity, entered our space and time. And so God is transcendent and immanent. God rules the universe in some kind of a way that is consistent. He's made this covenant with creation. He doesn't simply set up some kind of a mechanism to run things. But He's also built into the structure of the world how things can cause other things. And for me, a big element of Genesis chapter 1 is that God is declaring that things have being. God says, let there be various things. And so letting something be means He's created things with characteristics and with properties and with abilities to do things, not autonomously, but sort of, in a sense, relatively autonomous. To be an electron is to be what an electron does, and to go ahead and be that electron. To be a human being is to do what a human being does. Have choices and make decisions and go through life with all of our experiences. And so the things that happen in the world happen because God has let those things be and have their being. whatever goes on in terms of probabilities and randomness and chance and so forth, I would say that God still works with all of those things to bring about his purposes. He's not helpless and sort of caught by surprise, and then having to like always come up with plan C and D and E all the time. But he's somehow using and working with and guiding the processes of the universe. Polkinghorne describes this in a book called Science and the Trinity as a universe with an open process and a true becoming. God created a world with not only with being, but also with becoming. The world is a world that's under development, and God is working with all things to bring about his purposes. I don't think I've answered all of the questions about the indeterminacy, but those are some of my sort of thoughts about that in a preliminary sort of way. Okay, so now we're getting to something in quantum field theory, which gives me the opportunity to describe some resonances between how things in the world exist and how that might reflect and mirror and perhaps echo or resonate with how we actually also understand the nature of what it is to be human, and even something about the Trinity. So here we go. So now I'm going to describe for you how an electron goes from here to here. So for the quantum physicists in the crowd, I'm talking about the propagator of the electron. So how is it that an electron exists? What is an electron? What does it mean to be an electron? What is going on when an electron moves along through space and time? And this is what I've got on the screen here is a Feynman diagram with lots of solid lines with arrows, which represent electrons, and a number of wavy lines that represent photons. And every single intersection in this diagram is one where there's a line coming in and out, and then a wavy line. So that this diagram is one of the ways in which we could start with an incoming electron and end with an outgoing electron and connect them up with some of those photons. So one of the things that an electron can do is it can come along and it can like veer off over to the right here and emit a photon, a particle of light. And this electron, which has veered off this way, can turn again and emit another photon, and this photon goes along and produces a electron-anti-electron pair. So antimatter is on the screen here. We have situations where an anti-electron will combine with an electron and collapse and annihilate each other and produce a photon over here. And so this is sort of what the electron does. It kind of plays along with this possibility. And so one of the possible things that the electron could do in going from the left side of the screen to the right side of the screen is to do this sort of thing. So here's where there's an assignment for your children and grandchildren. You can say, well, see if you can find how many ways you could complete a diagram with incoming electron, outgoing electron, and simply connecting them up with these kinds of vertices. And you'll get them going on this for a while, and it'll take them a little while to list all the possibilities. In fact, it'll take them quite a long time because there's an infinite number of possibilities. You can see, for example, this line here of the electron, we could replace the whole diagram. We could replace this line with the whole diagram, shrink the diagram, put it right here, and there we go. There's yet another way that this electron could go ahead and behave in that way. So when we start counting the possibilities, there's really an infinite number of them. And these are the different kinds of things that the electron could do. So now the sort of final part of the story is not that the electron then has before it a bunch of possibilities and it chooses one of those and does that one, but in fact the electron is doing all of these things all of the time. So it does every possibility all of the time. This is called the sum over histories. The electron is actually doing all of the things that it could possibly do. And we know that's the case in part because we can, for example, put a barrier over here, and that's going to actually change whether the electron will make it through there. So putting a barrier somewhere off to the side actually changes the behavior of an electron going even, that doesn't seem like it goes there, but in fact it does. It goes everywhere. And so this is the nature of the quantum world. It has particles that do all of the things that could do all at the same time. And so the way that, one of the things that this changes about our perception of the world, perhaps, is that instead of thinking of a world where there are things in the world that interact with other things, perhaps according to some kind of law that God uses to govern those things, it's more like God is governing lawful things. That to be an electron is to be in relationship with all of the possible things that it could be in relationship with. So Prigogine and Stinger say something like this when they say, for an interaction to be real, the nature of the related things must derive from these relations, while at the same time, the relations must derive from the nature of the things. So to be an electron is to have these kinds of relationships, to the way that it relates to everything else. So perhaps this sounds sort of familiar. In fact, Maxwell, James Clerk Maxwell, who worked on electromagnetic field theory, thought about the same kinds of things. So Maxwell, let me just read a piece from Perspectives on Science and Christian Faith, which, by the way, is the peer-reviewed academic quarterly journal of the Canadian Scientific and Christian Affiliation and the American Scientific Affiliation. There's an article written now almost 30 years ago by Jim Neidhart, who is a historian of science, who dug into what Maxwell wrote and about his development of electromagnetic field theory. And he says, for Maxwell, central to the biblical understanding of the person is the reality of human relationships as an integral part of what persons really are. You as a person are not an isolated individual, like the Newtonian particle, separated from other autonomous particles, but are interrelated with others, your parents, your friends, even people with whom you disagree. These interrelationships constitute the very stuff of personal being. This deep appreciation led to Maxwell's development of the electromagnetic field in order to describe particles as never separable from their interactions. And this was long before quantum physics and long, of course, before quantum field theory as well. So the point is that Maxwell's thinking about humans and how they relate to one another as being integral to what it even means to be human, sort of doubled over into his thinking about how particles and fields exist in the world. Kind of an interesting echo, and of course not directly causal. It's not like we're saying because humans interact in this way, therefore electrons also do. It's not at all what he's saying, but there is interesting resonances. Colin Gunton, a famous Reformed theologian from the 20th century, wrote a book called The Promise of Trinitarian Theology, in which he says things like this. Modern field theory has led to the conceptual echo of Trinitarian theology and relativity theory and its developments. So there's this idea of a conceptual echo, and he refers to the Trinity. Of course, he's talking about a book called The Promise of Trinitarian Theology, but he refers a lot to science as well. And he says that science shows us these interesting echoes. God is Trinity. Father, Son, and Holy Spirit relate to one another in certain ways in this perichoretic dance of the Trinity, this dance of love, into which we as humans are also invited. And he says that that is somehow interestingly echoed in the way that particles and relate to one another, and how things happen in relativity theory as well. I'll skip the next quote there that maybe you had a chance to read. So I'm going to end with a couple of remarks about biophysics. So I mentioned perhaps that one of my fields of interest is in the theoretical and philosophical biophysics. And there's a sort of a research question or some speculative ideas I have about how it is that electrons, which are physical quantum behavior kinds of things, how are they open in some sense to the biotic world? So what is it about the physical properties of the electrons that allow them to be part of something bigger than being just electrons? So to be a biological organism, for example, or to be a cell, requires electrons, it requires atoms and molecules. Are there any physical characteristics of those atoms and molecules and electrons that are needed so that the biological functioning can actually be real? And so my thinking is that the indeterminism of the quantum world is somehow fruitful for the development of the biological world. That is, the physical principles of the world are just right so that the biological world can even be there. Like as we sit here in this room, we're able to digest our food in part because of the physical structures and physical behaviors of the quantum world. And in my reformational philosophy, this is described in terms of anticipation. So we have this idea that the physical world is sort of brimming with possibilities. The physical world is sort of saying, there's more out there in the world to do. And so life comes along the scene. In fact, God endows the world with living things, and those living things were sort of anticipated already just by the fact that the world has these physical properties of indeterminism. So I think indeterminism is needed for the biological world to function. That is, the biological world involves things like agency and things like processes happening in cells, which are actually, they have to be random. And so without randomness, there wouldn't be proper functioning of cells. You have to have proteins that are on the cell membranes and traveling along and bumping along and finding each other. And these are not sort of brought in, directed to where they're supposed to go, but they end up there randomly. And so this indeterminism is sort of fruitful and in terms of allowing the world to happen at the biological level. So there's something about the scales that hints at this, right? So the electron and atoms and molecules are at the right scale where quantum stuff can happen, and they're also at the right scale where biochemistry needs to happen. Some of you have taken biochemistry and you realize that it's the biological molecules that are moving around that are needed for life to function, and it may be that the indeterminacies of the quantum world are providing that opportunity through random processes. So now then I'm going to end, this is I think my last slide, where I'm going to talk a little bit about action in the world, so human action in the world, how do people act, and perhaps how does God act in the world as well. And one of my themes here is that created reality has many facets and levels to it. There's a physical level, the level of atoms and molecules, and the level of stones and waves and that sort of thing. And there's also a biological level. There's the biological realities, the biological facets or biological aspects of the world. There's also mental aspects, so we are able to think and so forth. In many cases of events that happen in the world, it's hard to just divide them into whether that's God's action, whether that's human action, or whether that's natural action. So, if Dick meets Jane, is that God acting in their lives to bring that about? Is that a natural event, like the fact that it was suddenly started raining and Dick had to step inside the restaurant and there met Jane, right? Or was that a human action where Dick, said, "I'm going to go find this Jane," right? Who's doing the action? And we can't divide actions into whether they're God's or ours or nature's in all cases. Although perhaps for insurance purposes, you somehow say this is an act of God in some cases. Although you might ask, if this tornado would have happened if the world hadn't been inflicted by, climate change, for example, which is maybe a human consequence of human activity. So all these things may be wrapped up anyway in some way. So when I think about how I act in the world and how you act in the world, we realize that all of the levels of the universe are functioning together in some way. So when I raise my hand, for example, am I micromanaging the electrons of my hand and arm and whole body to make my hand go up into the air? That is, am I doing things from the bottom up? Or am I doing things in this way? That is, my mental abilities, not at all connected to the physical reality, is sort of telling me I want to raise my hand, and then I raise my hand from the top down. I would say that neither of those two scenarios is really satisfactory to me, but somehow what's really going on is that all of these levels are functioning together. I raise my hand. It's not my mind that tells my body to raise my hand, but I, as a human being, with all those aspects, I raise my hand together. And all of the functioning that occurs across all of these levels that are present in the world at the same time. And so perhaps God's action in the world may also be of that same way. God isn't just moving around individual electrons in our brains and making us think different thoughts. He's just acting in the world. And I don't have an explanation of how he acts, but I think it does sort of span all of the levels that are found in the world. So with that, those are some of my thoughts about some connections between quantum physics and Christianity, some resonances, perhaps some challenges, and perhaps some ideas for further development. And I'll just leave on the screen here some suggestions for further reading if you want to do some more reading along these lines. I've mentioned John Polkinghorne a number of times. Here's his book called Quantum Physics and Theology. There's also Stephen Barr, who is a Catholic and particle physicist who wrote a great book called Modern Physics and Ancient Faith. And there's Hans Halvorsen, who's a philosopher of physics who works at Princeton, who wrote a really great review of Plantinga on Providence in Physics a few years ago in a journal. So there's some further reading, and I thank you for your attention, and I would like to entertain some questions.
Okay.
So the question is, is it possible that God could be fully transcendent, but yet still interacting with the world? I guess, but I think in terms of what immanence means, immanence is getting at is that God can be active and present within the world, and so the fact that God does act is part of what the definition of immanence would be.
So transcendence takes that out of...
Yeah, so if God were purely transcendent, God would be completely other than the world. So deism is an example of a transcendent, a fully transcendent, and completely non-immanent God, in which God created the universe, sets it off, and then is no longer concerned in any way with anything that's going on in it. So there are indications that Sir Isaac Newton was a deist in some way, and so that's not, however, the God of the Bible, who does interact in some kind of personal way, and then in particular even the incarnation of the second person of the Trinity joining, and becoming fully involved with the universe, and even now still having after the ascension, having brought into God's dwelling place, parts of this world, in a way that ties God's reality with our reality in deep ways.
Oh, okay, yes. Why do the effects of the quantum world not normally show up in our real world? And so, well, the effects of the quantum world are our real world, in a sense. So the fact that you're sitting in a chair without falling through it, even though it's made, 99.999999999% empty space, is a quantum effect. So the electrons don't fall into their nuclei, and the particles are repelling one another and staying in a good static state. Now, we don't think of that as a quantum phenomenon, but it is. But the kinds of things you're talking about, like uncertainties and wave functions and that sort of thing, why they don't happen in the large-scale world. Well, so here's a scenario, right? If I want to leave this room, I've got two options, one door over there and one door over there. And I'm, as a person, going to actually go through one door. I won't tell you ahead of time which. Actually, there's another set of doors over there. I'm going to leave you in suspense, to which door I'm going to go through. An electron actually goes through both doors in some sense and then recombines. I'm not an electron, and the reason is because I have many, many, many electrons. And so one of the reasons that the quantum effects don't appear at the macroscopic level is that there are many, many quantum particles, each doing their own little thing, and their net effect is to produce something which can't simply send part of itself through one door and part of itself through another door. So that's part of the story. Other parts of the story include the fact that the doors would have to be so close together for my wave function to actually be able to go through those two doors. And as it is, my wave function is so tiny, and those doors are too far apart. I'm not sure if I've answered that question very well, but that's sort of a hint at what's going on there.
Yeah. Earlier in one of your slides, you were talking about entanglement. You said that you might be able to explain that a little bit later. So
yeah. So at one point I said something about how the world is not reductionistic but holistic. In that sense, I think I was referring to that on this slide, perhaps. So I'm not an expert on entanglement, but here's what goes on. So when we create a quantum system, for example, just two particles that are nearby and interacting in a certain way, so that the state of the system can best be described in some sort of a overlap of two possible states. So suppose we have two photons, one spin up, one spin down. This is all kind of, I'm using some language loosely. But so suppose you have two particles, one spin up and one spin down. It could be this way or this way. So if we prepare the state so that it's 50% probability like this, 50% probability like this, and what if we now take that state of the two particles, which is a state which is a mixed state of those two, and then send the particles far apart from each other, so that even as they travel apart, they are still 50% this, 50% this. those two particles remain, in some sense, entangled. That is, they are going to be doing the opposite of the other all the time. Whatever's going on here, the opposite is happening over there. Those two particles have some kind of a way in which they remain connected, even though they're really far apart. And so it turns out that we've done experiments on this sort of thing where we do a measurement over here, and the kind of measurement that we do over here affects the kind of answers that we get by measurements over here, even if those are happening at the very same instant with not enough time for any signal to travel from one to the other. So that indicates something about the collapse of the wave function. When the wave function of the large system collapses, it collapses everywhere at the same time. So that's just a little bit about entanglement and holism, if that's what I think that's what I was referring to.
And a change on one end, is it equal on the other end?
Well, in a sense, equal and opposite in that particular setup.
Okay.
Yeah, and you can imagine different kinds of setups. So that's sort of the simplest possible setup. And we've done this sort of thing in labs where the distances between these are several kilometers, and we do the measurements within nanoseconds. So there's simply no time for any signal to travel. Okay, yeah. So the question is basically, how is it that classical pre-quantum physics understanding has been so successful, like sending the man to the moon, even though we now know it's been, that the world is understood better from a quantum perspective. And the basic answer is that the kinds of things that we're talking about, like rockets and tanks full of fuel and people and planets and these sorts of things, are large objects with many, many, many atoms and molecules. And I don't mean just many, many, but I mean many, 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 right? So 10 to the power of 30, 10 to the power of 32 numbers of atoms. So when you have many, many atoms together, each one is unpredictable, but as a whole, they're very predictable. And so the sort of demo that I had up here, it's very predictable after 2 half-lives how many there are. Even when there's 400, this is, I think, 400. And when there's 4 million, we can be even more precise. And the more there are, the more precise our calculations can be. Those individual probabilities turn into things that we can really precisely calculate. And people make money on this all the time. So casinos use the fact that even though the individual roll of a die is unpredictable, they know what's going to happen in the large scheme of things, and they're going to win, right? And actuarial science, people in life insurance, right? They don't know when any individual will die. From their perspective, it's random. From the person's own perspective, it's because of a particular disease they got, or a car accident, or whatever. But the insurance industry makes money because they have looked at these patterns of randomness and found those patterns. And so one of the things I would say reflects God's character too is that even though there is randomness on the individual level, that we can be thankful to God that there's this pattern of regularity that shows up on the larger scale. And that pattern of regularity on the larger scale is needed for larger scale systems not to depend so intricately on the individual tiny little variations. But yes, I also made a good point that quantum world is not irrelevant. I mean, many of our devices require quantum mechanics. The laser, for example, is a quantum mechanical device, and lasers have huge effects on all kinds of things. And I'm not going to even get started on what quantum physics has done for human society.
So at the beginning, you were talking about how things behave differently depending upon whether they're being observed or not.
Yes.
How would you know?
Yeah. So how do we know that things behave differently when they're being observed or when they're not being observed? So there's a famous two-slit experiment. So we send. So I mentioned that electrons also are waves, and so we can send a beam of electrons to a place where there's 2 little openings, and then we have a screen where the electrons land. And where the electrons land on that screen, we see a pattern which shows that the electrons are waves. So that the electrons show up here, not here, here, not here, here, not here, in a pattern which is only possible if those electrons are waves. And they're going through just one slit or the other, we would sort of think. And so then we ask the question, well, which slit is it going through? And if we watch which slit it goes through, and if we catch it on the way through, it fails to act
like a wave anymore. Now, if we watch it, it only lands there or there. It only goes through the one slit or through the other slit because you watched it go through the slit. If you stand back and don't watch, then it shows wave character. If you look carefully, you'll see that it shows particle character. So this has been done many times in many experiments, and it's quite convincing. Now, I suppose we are assuming there's regularity. We're assuming that the world would have behaved differently the second time if we weren't watching. It should have behaved the same way the second time if we also didn't watch. Right? Now, this world might be a really weird world where all kinds of weird things always happen, like when we watch the third time and the seventh time, this happens and that happens. But we assuming that the world has patterns of regularity, we realize that whenever we don't watch, it shows itself as a wave. Whenever we do watch, it shows itself as a particle. And so the question that we ask upon our observation changes the behavior of the particles. Yes, David.
Oh, could you explain the subjective participant again?
So there were two parts of that. One of them was the behavior of an electron depends upon whether the kind of observation that we are doing for it. And the second part had to do with the fact that the human observation sort of causes the wave function, which is the set of probabilities, to collapse down to just being one probability or one particular case. The second one assumes that the human observation is the only thing which can collapse a wave function, and that's the sort of standard Copenhagen interpretation of quantum physics. There are other ways, however, as well, and my approach to this would be that as long as some observation or some thing has happened which is on a large enough scale that can't be just flipped back to the way it was, so that is called the macroscopic irreversible registration of a quantum phenomenon. At that point, the wave function has collapsed. So in fact, I would say that it doesn't actually require the human to open the box to make the cat be dead or alive. In fact, the collapse has already occurred by the time the lever falls, because the lever down here is a large object containing moles and moles of atoms and molecules. So there's an irreversible registration of the quantum event that happened even when the lever fell, that didn't actually require the human to be involved. And so the second element, the collapse of the wave function, I would say doesn't really require the human, but there are some smaller scale cases where that would have to happen.
There's one perspective. Other perspectives that some Christians would have is that God is always acting and observing the universe, always making the wave function collapse. I would just say that probably in some cases, if there's not much between the activity and the human, then the human would be perhaps involved in collapsing the wave function. But the wave function collapses most readily when there's some large object that moves, because there's so many particles involved in that it's irreversible, and that is good enough to trigger that one of the possibilities has actually happened.
You were saying we've moved from thinking of ourselves as objective observers to subjective participants, but I don't see the subjectivity part of it. I mean, I understand the participatory part of it, that we can't learn something without affecting it, but I don't see how that makes us any more subjective.
Yeah, good point. So is it simply that we've gone? So we're no longer fully objective, but we are somehow involved. So in a sense, we are part of the universe as sort of subject to the same kinds of phenomena. So that's sort of what I mean by subjective. I don't mean that it's simply an individual's choice how to describe something in that kind of subjectivity, but just that we are also subject to the same behaviors that the quantum world is involved in, and we are involved in that way as subjects to the laws and affecting the thing that we're just otherwise observing. So yes, I guess there are different kinds of subjectivity where just each person thinks of it in whatever way they want. So I'm not saying that it's relativistic. Yeah. Maybe that's
all
not
I'm saying
quite.
is that I think your use of that term there is misleading.
Okay.
It makes people think you're
so it may be
something much stronger than you're really saying.
Right. And when drawing these sort of contrasts and the shifts in worldviews,
Not subjective like figure skating, judging a figure skating.
Right, not the same as judging a figure skating and that sort of thing, right? So, so yes, I mean, I guess I acknowledge that in drawing this shift in worldviews, it's not meant to be like absolutely everything has completely changed and there's no room for objectivity in science. There's plenty of room for objectivity in science, but on certain scales, we have to acknowledge some level of human involvement and human being subject to the same issues. Yes, thank you for that nuancing of my point.
So the question is indeterminism simply an actual characteristic of the universe,
right,
or is it simply a limitation of our ability to know because it's just too complicated and would require too much knowledge? So the definition of determinism I gave is an in-principle kind of definition. So in principle, if we knew everything about the universe right now, then we could, in principle, figure out what the universe will do in the future. A bit more precisely, what it means is that the future of the universe is determined by the present of the universe. It's not about our knowledge of the future necessarily, but it's just even what the future holds. So if the future of the universe is fully dependent upon and determined or settled by the present of the universe, then that's determinism. And so I would say that indeterminism is a real property of the world, that the world's future depends on more than just the present. There are possible options for the world to go in. And I guess that's an ordinary human experience, that if several times today I was walking along with Arnie on campus, and there was like a doorway over there and a doorway over there, and I wasn't forced into a doorway. I mean, Arnie didn't shove me into a doorway, but we walked along and I went one way and he went the other way. And so I chose to go that way, right? I wasn't forced. So that's an ordinary human experience, that we have choices, that we have free will. And so I would say that that's a property of the universe, and it's not only a limitation that we have in terms of our knowledge, because the definition I gave was not one of our actual ability to calculate the future, but of our sort of in-principle ability of figuring out the future. Does that answer your question?
Yeah. I think, the conclusion is not a forced conclusion. I think that there are legitimate ways that people could still argue for determinism, even based on what they know about the quantum level. I kind of follow John Polkinghorne on this, where he describes critical realism as being epistemology modeling ontology, so that what we know about the world describes something about the way the world really is. And so, as we've progressed through the 20th century and into the 21st, we began, I think, our thinking about uncertainties as being a human limitation. But as that's being probed more, we begin to, I think we've realized more and more that the wave function that is the collection of probabilities by which we describe the quantum level, that the wave function is, in some sense, a reality, not just something that describes describes probabilities, but it's a reality, and that reality sort of shows up in all kinds of ways, in overlapping wave functions, in chemical bonding, but then even into more and more examples of entanglement, where we have widely separated systems still exhibiting a common wave function, and so it just appears to be a natural conclusion for Polkinghorne and for me, following him, I guess, that our model, that if we want to separate our models from reality, maybe we can keep determinism. But I think the model for reality does describe something about the way the world really is, and that's just, to me, a more natural conclusion than to say that, well, maybe we'll eventually figure this out. We've encountered a number of cases where we looked, what if there are hidden variables? And we realize, well, okay, maybe there's hidden variables, but then we lose locality and causality. And for me, that's just not a place I would want to go necessarily, although I see that it's not a forced conclusion. So
I guess certainly classic and traditional Christianity would say that God is omnipotent, all-powerful, all-knowing, omniscient. And so God knows everything. But I guess when we say God knows everything, we have to be a bit careful, because we already mentioned that God doesn't know the color of the number 6, and so God only knows everything that can be known. And so my comment about God not knowing where the electron is and how fast it's moving is not a limitation of God's knowledge, but it's an assumption that our categories of knowledge apply in the same way to God. In fact, it's also a problem in terms of putting our categories of knowledge of the large-scale world down into the small-scale world. So we realize even when we study quantum physics that our categories of describing the world they have to come from study of that world rather than imposing upon the world our macroscopic knowledge. But yes, God, in a sense, is outside of time. But I also tried to illustrate that God is within time as well in some way. God is both immanent and transcendent. God, in his transcendence, I think, would know everything about the universe that can be known. You could ask, how does that relate to the future? And I guess there are different perspectives on that. Certain elements of Christian theology would say God knows the future, even if the universe is indeterministic. It doesn't mean that God can't determine the future or God can't know the future. But I guess God's knowledge of the future isn't necessarily dependent upon him knowing where everything is and how fast it's moving. After all, the locations and speeds are not necessarily what the particles really have. They are more human descriptions of the world.
The point about determinism is not so much that God doesn't determine the future, but the point about determinism is determinism says that the universe determines its own future. And so my perspective is that God determines the future, but he doesn't let the world determine its own future. So in a sense, quantum physics has shown that the world is indeterministic. In a sense, the world is open to influence from other places. And I guess we experience that ourselves, that the world's behavior depends on our action in the world. And I would say as a Christian, I believe that the world's future depends upon God's action in the world as well. I'm hesitant to say that God has the future already all fully locked into place. But that God is, I'm more comfortable with the notion that God works with and in and through all things to bring about his good purposes for everyone. And so, partly because I take seriously the idea of human responsibility, and I think there's a deep mystery between God's sovereignty and human responsibility, and I'm not comfortable in saying, so the answer to, is God sovereign or are humans responsible? The answer to that one is yes. So I don't know if I fully answered your question, but that's my thinking along those lines.
Thank you.
Does the indeterminacy of the quantum world cause the unpredictability of when and where of mutation? And if so, does this in some way let God off the hook for the mutations that cause disorders?
Okay, so the question basically is the indeterminacy of the quantum world important in mutations, for example? And if so, does that let God off the hook of problems, for example, cancer, right? And so cancer is often a result of some kind of mutation. I received some kind of mutation by a single photon that hit my back when I was 14 years old, and I got melanoma. Does it let God off the hook? Well, God created the whole universe, and so I don't think you can ever let God off the hook. But there are all kinds of things in the world that happen that we don't have good reasons for why they are that way. I think one of the basic Christian comforts is that God is with us, regardless of whatever situation we find ourselves in. And I don't think it's a matter of blame, although there's a standard understanding by many that the problems in the world, especially problems relating to human issues with things, is a result of the fall into sin. So I believe that the fall into sin is a real historical event and has real consequences for how humans relate to the world and how the world relates to us. But it is true that individual mutations are caused by quantum events.
So a single cosmic ray emitted by some individual atom in some star light years, millions of light years away, that happened millions of years ago, has traveled through space and has then hit, hits a molecule and changes the behavior of that molecule. And so as a result of that quantum event, I got cancer. And some of your friends died, right, of those individual single pieces. Yet, the Bible says that God knows and cares for every one of us, and God has his eye on every sparrow, right? And so there's a sense in which God is certainly involved on some deep level, and is not letting the universe just do its own thing per se.
Your comments on indeterminism sound more like open theism than Calvinism. I was just wondering how you would comment about that.
So my comments on indeterminism sounded more like open theism than like Calvinism, and I guess Lauren knows that I'm a Calvinist, and so how could that be? I would say this on the left side here, that kind of describes, in a sense, I think open theism is sort of on this side over here. Open theism says that God is totally, the future of God is undetermined. When I'm describing indeterminism, I'm not talking about the future of God, I'm talking about the future of the universe. And I'm not saying that the future of the universe is not determined at all, but I'm saying it's not determined by the universe. That is, knowing everything about the universe today isn't enough to settle what the universe will be like in the future. God could still be working to determine the future. God could have maybe already determined the future. That's not something that is touched by the topic of indeterminism. So it's possible, I think, to even be a hyper-Calvinist and say that every single possible thing that will happen in the future is already set by God, but to still be an indeterminist, where you say the universe doesn't determine its own future, but the future of the universe is determined by other things. By whether it's by chance events, whether it's randomness from our perspective, whether it's God acting from outside of the universe to bring about his purposes. So in a sense, I'm having my cake and eating it too, if you will. So this is not discussing in Reformed or in Calvinistic theology. There's talk about predestination, and this is it's a completely different topic than determinism, I would say.
So is there a difference between my definition of determinism and predestination? Yes. So predestination would say that there's different elements of predestination. One element of predestination might be that God determines everything. That might be one definition of predestination. I don't think that's a good definition, but that would be God determining things. And so determinism says that the universe settles what the future will be. The present determines the future. So predestination would be that God determines the future. Determinism says the universe determines its own future. So another definition of predestination is not so much that God determining everything about the universe, but that God determining something about about salvation of individuals. And that's sort of the more classic, I think, definition of predestination. So there's sort of three kinds of definitions going on. One, the two different versions of predestination and determinism. Does that help?
I think it was that isn't, as indeterminability being a property, isn't that applying our categories of knowledge to God in the same way that it would be wrong to apply it on a quantum level?
All right. So is our sort of category of indeterminism, if we apply that to God, we have to be careful, right? Rather than to just, it's one thing to apply it to us. But I guess even the way I described indeterminism is it wasn't so much about us, but just about the universe itself. So the universe's future, if that depends only on the present, then that's deterministic. But maybe the universe is dependent upon God in ways that don't depend just on the universe. So God could still determine the future of the universe, but yet the universe would still be indeterministic in the sense in which I defined it. That God could say, here's what the future is going to be. We can't, within the universe, tell what that future will be. in principle, even we can't tell, and the universe doesn't make what it becomes in the future, but God, in some way, makes that future. I think that indeterminism doesn't settle theological questions like the knowledge of God. I think it's possible to retain a view of indeterminism and still allow for the possibility that God knows every detail about the universe now and about the future. But there are also alternatives. For example, the one you mentioned, namely that the future doesn't yet exist, and so God not knowing it isn't a limitation on his omniscience, but it's just a category. However, I still want to take your sort of warning to heart that we ought to be careful in how we describe God's relation to the universe as if it's simply just kind of like our relation to the universe. So even when I described human action and divine action, I was trying to be careful to say this is like a stretched analogy, and clearly it's limited in its usefulness, and in terms of knowing about God, we have to know about God in ways that are consistent with his nature, with God's nature, rather than our own nature. Although there is a sense in which knowing ourselves, as John Calvin says, knowing ourselves can lead us to knowledge of God, and knowledge of God can give us more knowledge about ourselves. So there is clearly an analogy between our personhood and God's personhood in some sense.
This might be an oversimplification, but it seems to me that the development of Newtonian physics and the deterministic view of the universe was developed at about the same time as Calvinism and the doctrine of predestination. Now, is that a coincidence? And if not, was it the physics influencing the theology, or the other way around?
Okay, so that's a good
opinion on it?
It's an interesting observation, Ed, that Calvinism and Newtonianism sort of developed around the same time. I don't think there was much interplay between the two, but I haven't studied this matter. I think there are probably people before Calvin who thought about predestination in similar ways as well. I don't think Calvin was the first predestinationist, and I don't think that Newton was thinking about predestination either. But there may be, worldview, grand cultural ways of thinking of the world that were present in both the mind of Calvin and the mind of Newton and their contemporaries as they thought about these sorts of things. And I guess one of the other common connections between those two is some kind of a total confidence, right? We can describe physics exactly. We can describe God exactly, right? So getting rid of uncertainties and mysteries, these are both elements of Newtonianism and Calvinism in a sense. So anyway, those are interesting thoughts, and maybe there's a good master's thesis topic for someone in the audience.
I encounter a lot of kind of hardcore determinism among a lot of scientists, and I'm wondering where it's coming from, because it certainly isn't coming from quantum physics.
So I guess I don't have that experience myself. I've not really encountered people suggesting that the world really is deterministic.
It's a very, very common atheistic view today.
I'm not really familiar with it. I know that one of the ways in which people reinterpret quantum physics to allow for determinism is to say that every option actually does occur. So when we have a quantum choice to go one way or the other, then both actions occur, and the universe then splits and becomes, it's called the many worlds hypothesis of Everett, so that every action that we make, every decision that we make, both decisions occur, a new universe is formed where we enter in one or the other. And so when we look back, we see a certain record of decisions and actions, but if we look forward, every action and every possibility is there. I'm not comfortable with that from a theological perspective, and I think that there's no scientific merit in that idea either. If there's determinism creeping up in areas of science that are not aware of quantum physics, that would be interesting. I think there are many people who are not aware of quantum physics and its intrinsic indeterminism. There are other interpretations of quantum physics that do try to rescue determinism as well. where we've got the pilot wave from Bohr, for example, which says that it appears random to us, but it really isn't. I think there's a trade-off that we have to make, and one of the trade-offs is that we have to give up locality or causality. So if we want to allow for the possibility that events can make changes in the past, then we can save determinism somewhat, but I'm not willing to go there either. So there's all kinds of reasons why I'm not a determinist, and I'm surprised that there are many people who are becoming determinists now, even if they're aware of quantum physics. So I can't really explain the reason for that.
My question would be to either the atheist who's critiquing you for injecting Christian God into that gap, or to the New Age guru who is injecting his own worldview into that gap. Why the Christian God? Why do you believe the Christian God is behind the realities that we're not discovering?
Right, so that's kind of a long
question. Sorry.
Okay, that's kind of a long question. I probably won't repeat it, but maybe it'll become sort of clear what I'm trying to answer when I give what I hope will be some sort of an answer. So the God of the gaps idea basically is that if we don't understand something scientifically, well, we just say that God is involved in that. And the basic problem with that is that as science progresses, we do begin to understand things that we didn't previously understand, and so then God sort of occupies less and less space for explanation. The solution of the general God of the gaps problem is that God is involved in the whole show. So God created this whole universe, and He sustains the whole universe. He's always active in everything. He's not only working in the parts that we don't understand, He's also graciously given us the opportunity to understand certain parts, even sometimes large parts, of what is going on in the world. And so the explanations that we offer scientifically are not meant to sort of sideline God, but they're meant, in a sense, to complement God. So one of the interesting interesting ways of seeing this is thinking about a pie. There's a speaker I saw who spoke about eating pie, and which part of the pie belongs to God, which part of the pie belongs to science. Well, it's not like that. It's more like a layer cake. But the bottom layer is God in every piece, and science explains some of the top layer. And maybe science will understand more and more of the top layer, but God is always there in the whole bottom layer the whole time. So anything that we understand, God is involved in that. Now, on the quantum world and how the God of the gaps might apply there, I guess some people would say things like, well, I mentioned how the act of human observation caused the cat to become alive or dead, and that's called the collapse of the wave function. Some people would say that, well, we don't need the human observer to collapse the wave function. God collapses the wave function for us ahead of time, so that God decides what the reality of the cat or any other quantum world feature would be. I don't think that's a scientific claim, and scientifically we would just say we don't know what causes the wave function, how this transition from a wave function to an individual result occurs. I'm not satisfied scientifically by saying, well, this is where God then steps in. I would rather say that, as I've done, God sets up these patterns of regularity. He's faithful to them in His covenant to creation. Jesus Christ sustains all things, including the quantum world, including a world of probabilities where things are combinations of different things. Eastern mysticism has jumped on quantum physics to sort of emphasize and perhaps overemphasize the nature of the holistic character of the world, that things are interconnected. Now, in the quantum physics understanding, we know certain things interconnect with other certain things. Quantum physics does not give license to the Eastern mystic to say, yes, all things are connected with all other things in some sort of a consciousness field. So I think that's an illegitimate application of some sort of a popularization of quantum physics to make it sound like it endorses that religion. So I'm not sure if I really answered your question fully, but maybe I got somewhere.
So I want to understand what what angle or what particular thing in quantum physics would have the greatest explanatory power to kind of give us an evidence of the existence of God? Or
yeah, sorry, there is no such thing. I would not say that quantum physics gives us evidence of God. I would not say that quantum physics gives us new apologetic arguments. My main talk is about the fact that quantum physics can be understood coherently together with Christian theology to understand the world as a whole. I'm not making a claim that there's no other way of understanding, but I find echoes of what we see in Scripture found in the realities of this world. Those echoes are not proofs, they're not demonstrations, you know, some people would maybe argue, maybe claim that, oh, because there's randomness, there's no God, right? Well, I think I've tried to offer some good explanations how you can deal with randomness and still acknowledge the reality and common faithfulness of God. That's maybe a quick answer to that. Now, I think we'll have to call that the evening. Thank you all very much for your attention.